Yeah, this students, let us consider that a body is kept on the table surface as shown in the figure. This is the pulling force, and the body will tend to move in the direction of the external force applied on the body, right? That time, the force of friction is in the opposite direction. Weight is not shown here, right? Okay. Weight will be acting vertically downwards, right? This is the normal reaction. Now, the thing is that what is angle of friction? Angle of friction is the angle between the resultant of a force of friction normal reaction with the normal reaction, right? This is force of friction and the other one is normal reaction, right? What is the resultant of these two? Resultant of these two can be obtained by completing the parallelogram and the diagonal of the parallelogram. This is what is the resultant of these two, right? So the resultant of force of friction normal reaction, what angle it makes with the normal reaction, that means this angle, this is what is called lambda. Lambda, I think you are able to see lambda here, right? This is lambda. Once again, I will write very clearly, this is lambda. The angle between the normal reaction and the force of friction. Sorry, angle between the resultant of uh, a normal reaction and force of friction with the direction of normal reaction. So with the normal reaction, what is the resultant is making an angle that is called lambda, right? This is what is called angle of friction. From the figure, if it is if this is Fs, this also will be Fs only. This also will be Fs only, right? Therefore, from the figure, we can suppose this is O, and this is A, and this is B, and this is C. OC is the resultant of uh, normal reaction and force of friction. Because when two forces are acting at a point, then the resultant of these two can be obtained by the diagonal of the parallel. So diagonal gives the resultant of R and Fs. What is R? Normal reaction. What is Fs? Force of friction. What is the angle made by this resultant OC, vector OC, with the vector R? That is what is called angle of friction. From the figure, we can write tan lambda is equal to Fs divided by R. Fs divided by R. R is the normal reaction. F is the force of friction. But everybody knows that we have already studied that Fs by R, the ratio of force of friction to normal reaction, is called a coefficient of friction. Coefficient of static friction. Therefore, we can write tan lambda is equal to mu s, we can write. So this is a very important relation, right? So tan lambda is equal to mu s. That means tan of the angle of friction is equal to coefficient of static friction, right? This is one thing. Other thing, what I want to tell you is about angular repose. Angular repose. So angular friction, I think you understood angular friction, right? Okay. Next is angular repose. Angular repose is the case when angle of friction and angle of repose. Next is angle of repose. Angular repose. In this case, we have to consider an inclined plane. What is an inclined plane? A plane which makes an angle theta with the horizontal is called inclined plane. So on this inclined plane is make an angle theta with the horizontal. A body is placed there. A body is placed as shown in the figure. Am I correct? So this body, when it is placed uh, 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 on the inclined plane, and this angle is go on increasing. Angle is go on increasing. This angle made by this inclined plane with the horizontal go on increasing. Suppose that there is a hinge here. This can be again lifted up, so that at a particular value of the angle between the horizontal and this inclined plane, the body will be on the verge of motion on the surface. That angle is what is called angular repose. So angular repose is the maximum value of angle between an inclined plane and a horizontal, such that the body is on the verge of motion. Body is not moved. Body did not move till now. But by increasing the angle by a very small value, we can judge that the body will be just going to slide. But don't allow the body going to slide. But it is on the verge of sliding. At that time, what is the angle between the horizontal and the inclined plane? That angle is called angle of repose. Understand? Okay, this is the condition. So angular, suppose this is the body is kept on the table, kept on the inclined plane. Various forces acting on the body are like this. See, the weight of the body is W is equal to mg is acting vertically downwards. Okay, then normal reaction is acting like this, and this mg can resolve into two components. One is along this direction, make an angle theta, because when the inclined plane fall on this one, then theta becomes equal to 0. When the incline is taken up, then this line will make an angle theta. As this angle also will be theta. If this is mg can resolve into any vector quantity can be resolved into two components in two dimensions. This is equal, make an angle theta with the mg, the component of mg will be equal to mg cos theta. Another one is perpendicular to that. This is equal to mg sine theta. Remember that. The body is sliding downwards, then force of friction is acting along this direction. This is what is called a static friction. You understand? This is capital R. Everything okay. Body is not moving. When the body is not moving, every forces are balanced. That means Fs is equal to mg sin theta and R is equal to mg cos theta. When the body is not moving, various forces are acting on a body and the body is in equilibrium. Then the uh, then all the forces are balanced. This vertical forces are balanced and also this forces also balanced. Fs and mg balances and R and mg cos theta also balances. Am I correct? So from this figure, this is very important how the variation of the variety of forces acting. Mg is acting vertically downwards. Mg can resolve into two components. One is like this and other is like this. These two forces are orthogonal components. Component of Mg. One is Mg cos theta and other is Mg sin theta. But the angle between these two, 90 degrees. Because orthogonal components are components of vector always perpendicular to each other. Am I correct? Now, from the figure, what we can write is Fs is equal to, right? Fs is equal to mg sin theta, I can write. And also R is equal to mg cos theta, also I can write. Therefore, Fs by R, this is equation 1, this is equation number 2. 1 by 2, we will get Fs by R is equal to mg sin theta divided by mg cos theta. Mg and mg cancels, right? Then we can write Fs by R. Fs by R is equal to mu s. So mu s is equal to sin theta by cos theta is equal to tan theta, where theta is the angle of repose. So angular repose, the term is used when the body is kept on an inclined plane and the plane, the angle between the inclined plane, the horizontally going on gradually increase. At a particular stage, the body starts sliding over that. That body is on the verge of sliding over the inclined plane. That time, the angle between the horizontal plane and the inclined plane is called angular repose, right? We have found that tan theta is equal to, already we have found tan lambda is equal to mu s. Tan theta is also mu s. Therefore, angular repose is tan theta is equal to, right? This is equation number 1. Already found what? Mu s is equal to tan lambda also. We have already discussed it. Therefore, this is also mu s, this is also. Therefore, tan lambda is equal to tan theta, or theta is equal to lambda, or lambda is equal to theta. That means actually angular repose is equal to angular friction. This is a very important result that we have come to. What is angular repose? Everybody knows, right? Okay. So this is the class today is about, and tomorrow we will come with another topic related to force of friction. Till then, bye bye.